Hello everyone, welcome back to this week's algebraic graph theory seminar. This week with Linz, he's going to talk about L system and then the Lovász number.
Yeah. Okay. So thanks again for the invitation to speak. So I'm going to talk about some ongoing work I've been doing with L systems and the Lovász number. I'd be happy to receive any feedback you might have consequently. Okay. So, all right. So to put some context in for the talk, I'm going to start off not by talking about either the Lovász number or about L systems, but instead I'd like to introduce something that I'm sure many, if not all of you, have seen before: the Hofmann bound. So just generally speaking, I'm going to assume that G is a graph on n vertices. And the eigenvalues of the adjacency matrix are always going to be labeled with lambda 1, lambda 2, lambda n in non-increasing order. And so whenever I talk about the eigenvalues of a graph, it'll always be in reference to the eigenvalues of the adjacency matrix. Okay, so the Hofmann bound is, so let's assume G is in fact a regular graph. Then we get an upper bound on the independence number, the maximum size of an independence set, in terms of the smallest eigenvalue, the largest eigenvalue, and the number of vertices. So these are all fairly easy to compute, whereas the independence number is actually quite hard to compute in general, also quite hard to approximate in general, actually, as well, assuming certain widely believed conjectures in complexity theory. But anyway, so that's part of the utility of the Hofmann bound. So to frame the discussion as well, I'm going to sketch the proof of the Hofmann bound. I'm sure a number of you have seen this as well, but it'll be useful to introduce why I would care about the Lovász number, for example. So here's the sketch of the proof. Let's define this matrix M to be this particular matrix, A, the adjacency matrix, minus lambda n times the identity matrix, minus lambda 1 minus lambda n over M times J, where J is the n by n all ones matrix, and J will be seen a few more times in the talk. It'll always be the n by n all ones matrix. So a fact that I'm not going to prove in any detail is that M is in fact a positive semi-definite. You can figure out what the eigenvectors of M are by the fact that A is regular. So the all ones vector is eigenvector also for J and for I. So then you just compute all the eigenvalues you can get what the eigenvalues are, at least bounds on them, and they'll all be at least 0, which implies that the matrix M is positive semi-definite. And since M is positive semi-definite, another equivalent characterization of that is if you take any vector x and look at the quadratic form associate x transpose mx, well, that's always going to be at least 0, and x transpose mx, when written out, is this expression x transpose ax minus lambda n x transpose x minus lambda 1 minus lambda n over n x transpose jx. Okay, so that inequality I've rewritten up here, and the point now is, remember, we're trying to get an upper bound on the independence number. So we'll take any independent set S now and let little s be the characteristic vector of that independent set. Well, since S is an independent set, if you look at what S transpose AS becomes, it's just literally you sum up over all vertices U and V of A sub UV times SU times SV. So if U and V are two adjacent vertices, SU times SV is going to be 0 because we're looking at an independent set. If U and V are not adjacent, then this is going to be 0 by the definition of the adjacent matrix. So you're just summing up a bunch of 0 terms. So now if I put x equals S into this inequality, I'll get 0 here, negative lambda n times the size of S here, and minus lambda 1 minus lambda n over n times the size of S squared there. So I get this inequality, and if I just rearrange this inequality a little bit, move some terms around, I'll get Hofmann's bound out of that. Okay, so that's the sketch of how the proof of Hofmann's bound goes, and the point I want to make is that we used really two properties of the adjacency matrix in the previous proof of the Hofmann bound. The first property, somewhat implicitly, more in the fact that we said that M was positive semi-definite, is A is symmetric and it has constant row sums. This is also a consequence of A being a regular graph. And the other, maybe more crucial property, so from the thing in red on the previous slide, was that A A sum uv equals 0 whenever u is not adjacent to v. Okay, so what we'll do now is we'll just say that any matrix which satisfies these two properties for a graph G is just going to be a pseudo adjacency matrix for the graph G. Okay. The point of this is, well, you can run the exact same argument we just did for the Hoffman bound through, assuming that's constant row sums and positive constant row sums, and that it's 0 whenever u is not adjacent to v, and maybe 0 along the diagonal too. If you run through the exact same argument, it works perfectly fine. So Hoffman's bound actually holds more generally for any pseudo adjacency matrix of a regular graph G with those So here's the restatement, and the only difference now is that it also holds for any pseudo adjacency matrix. So in principle, what you could do is you could try to get better and better upper bounds by for alpha of G simply by trying out different pseudo adjacency matrices to see what might give you a good bound for the independence number. Okay, of course that leads to an obvious question. Well, how do you pick a good pseudo adjacency matrix? We probably don't want to just try a bunch of pseudo adjacency matrices. You probably want to figure out how can we find the best possible bound in some reasonable way. Well, there's probably a number of ways you could answer the question of how you could obtain the best possible bound from pseudo adjacency matrices. But one way that I think is a good answer is you use the Lovász number. Okay, so here's the definition of the Lovász number. There's many different ways you could define the Lovász number of a graph, but this one will be particularly useful for us. So we'll let G be an invertex graph. We don't need to assume that the graph is regular. This definition works for any graph at all. So now for any matrix A, the largest eigenvalue is just going to be denoted by LEV of A. The Lovász number, well, that can be defined to be the minimum. So over all symmetric matrices, which are 1 on the diagonal and one whenever two vertices are not adjacent to each other. So among all matrices which have these properties, the Lovász number is the minimum of the largest eigenvalue over all of those matrices. Right. So, and again, for the matrix, that's its rows and columns are being indexed by the vertex set of the graph. Is the point? Okay. All right. So that's one definition, and now I'd just like to recall some of the the key properties of the Lovász number, just to put in the context. So you might recall the definition of the Shannon capacity of a graph. So now I'm looking at the independence number of the strong product of a graph with itself k times, and then if I look at that raised to 1 over k power, take the limit of that, that's equal to the Shannon capacity. This comes up in a communication complexity, as the name Shannon capacity might suggest. So, and then one of the key theorems that Lovász proved about the Lovász number is that, well, this expression, the Shannon capacity, is an upper bound for the independence number, right? Because you could just take k equals 1, for example, in this supremum definition. But also the Lovász number is an upper bound for the Shannon capacity, and this is particularly nice because, like I said before, the independence number is very hard to compute. Also, in general, very hard to approximate, most likely. The Shannon capacity, there's no known algorithm to compute it that definitely converges in a finite amount of time. But on the other hand, this quantity here, the Lovász number, it's actually computable for any graph in polynomial time up to arbitrary precision, because it can all equivalently be written as a semi-definite program. So here's how it goes as a semi-definite program. You could take, so G is an invertex graph. Now we'll take B to range over all positive semi-definite matrices, which are 0 whenever I is adjacent to J. Again, the matrices are indexed over the vertices of the graph. And then trace of B is equal to 1. So there's some sort of linear condition on the sum of the diagonal entries of the matrices. Then you can define then another equivalent way to define the Lovász number is it's the maximum over all these positive semi-definite matrices subject to these conditions of the trace of B times the all ones matrix J. So this writes it as a semi-definite program, which again means that it's computable in polynomial time up to arbitrary precision, which is nice when the other two quantities it's bounding are both very hard to compute in general. Okay, so so yeah. So Lovász was able to use this Lovász number in his original paper to famously determine the Shannon capacity of the 5 cycle, for example. Okay, and we'll be interested in different graphs for which the Lovász number also works very well, and for which it also, as a byproduct, happens to compute the Shannon capacity of those graphs as well. All right, but what's the connection to pseudo-adjacency matrices? Well, basically, the point is that the Lovász number, in some sense at any rate, gives you the best bound for the independence number that you could possibly attain by using pseudo-adjacency matrices. And so this is a theorem that, again, for Lovász. So G is now a regular graph with these eigenvalues. And then the Lovász number is bounded above by, well, the right-hand side of the expression is what you get from the Hoffman bound. So particularly this is a somewhat stronger inequality than the Hoffman bound is because alpha of G is also bounded above by the Lovász number. Okay, and I'm just saying with eigenvalues, so I'm just talking about the adjacency matrix, but the proof that I'm going to sketch the proof of how this goes as well. And again, the proof will work for pseudo-adjacency matrices perfectly fine. Okay, so here's the sketch of the proof. So let's consider matrices of the form J minus XA, where X is a positive constant some positive number that we'll choose later. The point is that J minus XA will satisfy the conditions for the definition of a Lovász number. So if you remember that, so the definition of Lovász number, remember we were looking at all matrices which are symmetric. J minus XA is going to be symmetric because J and A are both symmetric matrices. And we want the matrix to be 1 on the diagonal. Well, J is 1 everywhere, so it's 1 on the diagonal, and A is 0 on the diagonal. So J minus XA is 1 minus 0 or 1 on the diagonal. And we also want the matrix to have entry 1 whenever I is not adjacent to J. Again, the matrix J is going to be 1 everywhere. And then because A is the adjacency matrix, it's going to be 0 whenever I and J are not adjacent to each other. So the matrix J minus XA is again going to be 1 minus 0 or 1 everywhere. So matrices of that form perfectly well suit the definition of a Lovász number. So in particular, since the Lovász number is the minimum over all of those matrices, it's less than or equal to the largest eigenvalue of the matrix J minus XA, where you can choose X to be any positive number. Okay, now the eigenvalues of J minus XA can actually be computed. I'm going to sort of skip over that statement, but yeah, but basically they're just n minus x lambda 1, so the n comes from J, and then negative x lambda 2 up to negative x lambda n. So which one of these is going to be the largest? Well, it's either going to be n minus x times lambda 1, this first one here, or it's going to be the largest over all of these guys, the remaining ones. So the largest of all those would be negative x times lambda n. Okay. Well, so one way we could get a bound is we could choose X so that these two are equal to each other. In particular, that means we just solve this equation. X would be n over lambda 1 minus lambda n. And if we now just substitute that back into here, that would give us a bound that the Lovász number is at most, again, negative lambda n divided by lambda 1 minus lambda n times the number of vertices. Okay, so yeah, so the Lovász number already. So again, the point of that is that you can get sort of the best possible bound you could obtain from pseudo-adjacency matrices by computing the Lovász number of the graph, of the associated graph. Okay, all right. So that's the Lovász number. I'm going to now talk about applications of the Lovász number to L systems, but I'm going to first talk about specific examples of L systems. And in particular, I'll start by recalling a very famous theorem, the Erdős-Corrado theorem. I'm sure not all of you have seen this before as well. So So we'll say that a family of sets F is intersecting. If any two sets in the family have a non-empty intersection, then the theorem proven by Yiddish, Cohen, Rado is if you've got a K-uniform set intersecting family where all the sets are contained in a ground set of size n, then the size of F is at most n-1, choose k-1, and we need to assume that n is sufficiently big. In this case, sufficiently big means at least size 2k. Okay, so this upper bound, it's also tight because in particular, you could just take the family of all k element subsets, which contain the number 1, for example, and then that's going to have n-1 choose k-1 sets in it. And in particular, there's also a uniqueness statement of the Ayers-Corrado theorem that these are the unique families if n is strictly bigger than 2k. I'm not going to prove the uniqueness, but I'll sketch one argument for proving this upper bound. There's at least half a dozen proofs of the Ayers-Corrado theorem by now, but one of them uses the Hoffman bound, and in particular, it uses the Hoffman bound on the Kneser graph. So call what the Kneser graph is. So its vertices correspond to k element subsets of a set of size n. So there's n choose k vertices in particular, and two vertices are going to be connected by an edge if and only if A intersect B is just equal to the empty set. The point is, well, independent sets in the Kneser graph correspond to intersecting k uniform families. All right. Okay, so we could use the Hoffman. So you could use phrase in the Hoffman bound, or you could do, or as Lovász pointed out, you could also use that to compute what the Lovász number of the Kneser graphs are. So the eigenvalues of the Kneser graph are these these quantities here, -1 to the I times n minus k minus I, choose k minus I ranges from 0 to k. So alpha of g is definitely at least n-1, choose k-1, right? By our previous example of just taking all k element sets which contain the element 1. It's bounded above by the Lovász number, and then the Lovász number by the theorem we previously proved, or just by the Hoffman bound even, is at most negative lambda n divided by lambda 1 minus lambda n times the number of vertices. The number of vertices is n choose k. The smallest eigenvalue is obtained when I is equal to 1, in which case you get negative of n minus k minus 1, choose k minus 1. So the negative of that would give you n minus k minus 1, choose k minus 1 here. The largest eigenvalue is when I is 0, and then you get n minus k, choose k. Then a little bit of algebra says that you can simplify this expression down to n-1, choose k-1. So in particular, this doesn't just show that the maximum size of an intersecting family is n-1, choose k-1. It also shows that the Lovász number and the Shannon capacity of the Kneser graph are equal to n-1, choose k-1. Okay, all right. So we could go even further than that. What about T-intersecting families? Okay, so we've dealt with intersecting families. Now, T-intersecting family just simply means that every two sets in the family are going to intersect in at least T elements. Okay, so there is a version of the Ayers-Corrado theorem for T-intersecting families, and it was proven by Wilson. So what Wilson showed is, so if F is T-intersecting, then for n at least quantity T plus 1 times K minus T plus 1, F has size at most n minus T, choose K minus T. Again, the sort of trivial example of a T-intersecting family is you pick a set of elements of size T, and then just take all K uniform sets, so all sets of size K, which contain that fixed T set. So this in particular is the best possible bound, and moreover, this bound here on n, this range on n, is also tight. There are examples which are better than this construction if n is smaller, and we'll talk about that in a couple minutes. Okay, so if you wanted to mimic the proof by Kneser graphs, well, one thing you could do is you could say, well, let's define the T-Kneser graph, which I was called G of nkt, as a graph whose vertices again correspond to k element subsets of a set of size n, and you put edges now between two vertices if they're corresponding sets, have an intersection size at most T. So again, the point of this definition is that T intersecting families are going to correspond to independent sets in this T Knaser graph. Well, you can do this perfectly fine, and then you can, figure out what its eigenvalues are, run through the computation, and then you'll get some sort of bound from the Hopman bound. The problem, though, is just using the Hopman bound for the adjacency matrix won't give you a tight upper bound. So what Wilson did was he constructed a suitable pseudo-adjacency matrix, which I'm not going to write out in any detail here, for the T Knaser graph. And that suitable pseudo-adjacency matrix that he constructed also does in fact show that the Lovász number of this T Knaser graph, G of A and KT, is also equal to n minus T choose K minus T, whenever n is at least T plus 1 times K minus T plus 1. And it's not usually phrased in terms of the Lovász number, but Wilson himself even noted that in his original paper that he was equivalently computing the Lovász number of this associated graph. Okay, and of course the Shannon capacity is also computed by because it's sandwiched in between all these inequalities. Okay. All right, so that's. Okay, so that's a couple examples we've seen where, so we can use the Lovász number or do something equivalent in terms of finding suitable pseudo-adjacency matrices to get us the independence number of a graph very precisely. So can we do this in general? So in particular, in this T intersecting family case, what about values of n that are smaller than T plus 1 times K minus T plus 1? What are the maximum size intersecting families in that case? Well, you can do the same thing. You can define the same T Knaser graph. And again, independent sets in that T Knaser graph are equivalent to T intersecting families. So the answer for the maximum size of an intersecting family was given by the complete intersection theorem of Alsvede and Khatchatrian. So there's a whole collection of different families that are possible. So in particular, you look at all. So for any I, you look at all families. You look at all sets F which contain at least T plus I of a fixed set of T plus 2I elements. So we'll just take it to be the set of integers from 1 up to T plus 2I. And then the maximum over all of these families gives you the maximum size T intersecting family. So in particular, if I is 0, you just get back to the trivial T intersecting family that was best possible for n bigger than or equal to T plus 1 times K minus T plus 1. Okay, so sort of what got me first interested in these questions was I was thinking about could we give an algebraic proof of the Alsvede-Khatchatrian theorem? So along the lines of what Wilson was doing, constructing a suitable pseudo-adjacency matrix. Would it be possible for us to, come up with some very clever pseudo-adjacency matrix, which would imply this result of Alsvede and Khatchatrian? The original proof was combinatorial in nature. Okay. So can we find a proof like this? Well, let's look at one example. Let's take n to be 11, k to be 5, and t to be 2. Well, the complete intersection theorem tells us what the independence number of the associated T Knaser graph is. And it's equal to the size of this family here, and the size of this family here happens to be 91. But on the other hand, the Lovász number of the graph is 105, which is bigger than 91. So no suitable pseudo-adjacency matrix can exist for this choice. And you can try other choices as well, and you'll see that there is a gap between the Lovász number and the independence number for smaller values of n in general in any case. So if we want an algebraic proof of the Alsvede-Khatchatrian theorem, we're going to have to do something besides something other than finding a suitable pseudo-adjacency matrix, and the Lovász number guarantees that won't work, which saves us quite a bit of effort. Okay, all right, okay. So part of the talk was about L systems. So if you haven't seen L systems before, well, Erdős-Corrado and T-intersection Erdős-Corrado are concerned with special cases of these L systems. So what an L system is if you give me two positive integers n and k, and then you take some set of integers L between 0 and k minus 1, well, an L system is just a collection of sets F that are k element subsets of the set of size n, such that if I take any two distinct sets in the family, their intersection size is going to be contained in the set L. So, for example, intersecting k uniform families correspond to L systems where L is the set of integers from 1 up to k minus 1. T intersecting families correspond to L systems with L being t plus 1, all the way up to k minus 1. Okay, so all right, okay, all right. So that's what L systems are, and we can sort of do a similar thing to what we were doing previously with Knaser and T Knaser graphs, and define what I'm going to call generalized Johnson graphs. So again, n and k are positive integers. L is some set of integers between 0 and k minus 1. The generalized Johnson graph is going to be a graph whose vertices, again, are the k uniform k element subsets of a set of size n, and I'm going to put an edge between two vertices if their corresponding sets have intersection size not contained in L. And if L happens to be, you're just missing one intersection size, let's call it little l, then I'm going to maybe somewhat confusingly use the notation g of nkl in place, g of nk little l in place of g nkl, so swapping it around. So the name generalized Johnson graph, well, part of why I picked it was so. I'm not going to mention, I didn't write this anywhere specifically in the talk because it's not strictly necessary, but these generalized Johnson graphs correspond to unions of classes of graphs from the Johnson scheme, which is a well-studied association scheme. So we're looking at a union of classes of graphs from the Johnson scheme. So these are generalized Johnson graphs. And so, yeah, so L systems are equivalent to independent sets in unions of classes of graphs from the Johnson scheme itself. Okay, so that's not strictly necessary for the rest of the talk, but that's where the name comes from, and also where some of the techniques used to study it also are also going to end up coming from eventually, probably. Okay, so yeah, okay, yeah, all right, so okay, so we've seen that Lovász numbers don't always give the independence number of a generalized Johnson graph. We've seen it doesn't work if n is small for the T Knaser graph, for example. But unfortunately, the Lovász number can be a really bad approximation for the independence number. And I'm going to give an example now okay, so this example's phrased, so this theorem's phrased a little more generally, but the example will come from generalized Johnson graphs, and in particular, so for any epsilon bigger than 0, there's an explicit construction of a graph on n vertices whose ratio between the Lovász number and the independence number is something is at least on the order of n to the 1/2 minus epsilon. Okay, so all right, so that's a fairly large ratio, and the important and maybe the interesting part is the explicit construction part, from which will be from a generalized Johnson graph. So for random graphs, if you just take a look at the Erdős-Renyi graph, Erdős-Renyi graph with p equals 1/2, for example, it's known that the Lovász number is on the order of square root of n with high probability. We could say more about the constants, but I don't care about the constants for the purposes of this talk. And the independence number is on the order of log of n with high probability. Again, I don't care particularly about the constants. The point being that there is quite a large ratio expected in general for the Lovász number and the independence number, but it seems hard to give an explicit construction of a graph on n vertices. I mean, there are randomized constructions that give even larger ratios than this, but I haven't seen any explicit constructions which give this large of a ratio. Okay, so as I said a few times now, the construction comes from generalized Johnson graphs. So in particular, I'm going to be looking at the graph g of n 2l plus 1l. And so the number of vertices is n choose 2l plus 1, k is 2l plus 1, and then we're missing an intersection of size l. Okay, so Okay, so the Lovász number of this graph, which I'll talk about how this is shown, is on the order of n to the 2l divided by 2l plus 1, while the independence number is on the order of n to the l divided by 2l plus 1. Okay, and this, so assuming we can show these two properties, this will give the promised explicit construction. And the point is that, well, if I look at the ratio between these two things, 2l minus l is l, so l over 2l plus 1. The difference between 1/2 and l over 2l plus 1 is this 1 over 4l plus 2. So if we pick l sufficiently large, we can make that smaller than any epsilon that we desire. Okay. All right, so now I'll justify these two properties of the graphs, and so I'm going to instead talk about just general K first. So in particular, if I'm just missing out one intersection size L, that corresponds to one class of the Johnson scheme, and those graphs happen to have the nice property that they're regular, but they're also edge transitive, and the edge transitivity means that we can use the result of Lovász to show that, well, the Lovász number of those graphs is actually equal to the bound you would get from the Hoffman bound. So the negative of the smallest eigenvalue divided by the largest eigenvalue minus the smallest eigenvalue times the number of vertices in the graph. Well, so the eigenvalues of this graph are in fact known. So J ranging from 0 to K, and then you can plug 0 up to K into this, and you'll get, these are two different expressions for that. The point is that these come from parameters of the Johnson scheme. But anyway, the point is that they do exist. There are these sums you can write down for what the eigenvalues of the graph in fact are. Okay, so the largest eigenvalue is going to be when J is 0 in the previous expression. So it'll be this quantity. And then if we're assuming K and L are fixed and n is going to infinity, then this is going to be something of the order n to the K minus L, times some constants that I don't care, that are not important. What about the smallest eigenvalue? Well, there's a recent result of Brown, Schalba, Ehringer, and McGinnis, which shows that for n large enough, the smallest eigenvalue is going to be obtained when J is L plus 1, and then you can compute that's going to be of the order of n to the K minus L minus 1, again, as n's going to infinity, n's getting large. So what that means, if you now put everything together, is so the number of vertices in the graph is of the order n to the K, and then the ratio negative lambda n divided by lambda 1 minus lambda n is going to be of the order 1 over n. So 1 over n times n to the K, it gives you something of the order n to the K minus 1. Okay, so that's the justification for the Lovász number computation. The independence number of these graphs has been well studied. It's a result of Frankel and Fioretti that for any K and L, assuming K and L are fixed and n's tending to infinity, the independence number is equal to is on the order of n to the max of K minus L minus 1 and L. So actually weaker results would suffice. So results of Frankel and Wilson, for example, would suffice, but this does work for all K and L. So if K is 2L plus 1, which is what we had before, then the Lovász number by the computation on the previous page is going to be of the order n to the 2L, while the independence number is on the order of n to the L, right? If I put K as 2L plus 1 here I'll get something on the order of n to the L. And then, well, remember that the number of vertices is not n, and the graph is not little n, it's n to the 2, it's on the order of n to the 2L plus 1, so which is where the ratio comes in from that. Okay, so that's the construction of a large gap between independence number and Lovász number for the generalized Johnson graphs. Okay, so where do we go from here? Well, so far I've just been talking about generalized Johnson graphs which correspond to L systems which miss one intersection size. Well, what about general L systems? Well, I conjecture the following for the order of magnitude. So let's say that n and k are positive integers. L is some set of integers between 0 and k minus 1. If F is an L system and k and L are fixed, n's tending to infinity, then I conjecture that the Lovász number of G of NKL is on the order of n to the L, n to the size of the set L. Okay, So I haven't seen any results about this in print before, or any conjecture about this Lovász number either. So some evidence. Well, by the work I've shown previously, it's true if L is equal to the set of integers from 0 to k minus 1, and then take out any number L, any number little l. It's also true for the for the Knaser graph, T Knaser graph, and it's also would be of the same order of magnitude as two general bounds for the maximum size of an L system, which are due to Deza, Erdős, and Frankel, and Ray, Chowdhury, and Wilson. So there's two general bounds that are both of the order n to the L for general L. So this would be of the same order of magnitude as the two known general bounds for the maximum size of an L system. And I don't think, and the Lovász number would not be better in general than either of these bounds. It would also not be worse in general than either of those bounds either, assuming that this conjecture was actually true. Okay, so we could also look at the opposite question of so we've talked about large ratios between the independence number and the Lovász number. What about examples where the independence number and the Lovász number are in fact equal, and in particular would also give us a precise value for the Shannon capacity of the associated generalized Johnson graph? Well, the Erdős-Corrado theorem for both its regular form and for the t-intersecting form implies it's true for L being t plus 1 up to k minus 1, and for a sufficient bound on n. So are there other examples of graphs? Are there infinite families of graphs? I was able to construct one infinite family of graphs for which this equality does hold. I think at least one more example should. I think there's at least, I have conjectured that of a different family of graphs for which this should also hold, and it'd be curious to figure out which generalized Johnson graphs this holds for n tending to infinity, let's say, and fixed k and L. Okay, so I've been focusing on generalized Johnson graphs because I started being interested in finding maximum size of L systems, but you could also study the Lovász number of unions of classes of graphs in other association schemes. So maybe the most straightforward example would be, you can define analogs of L systems for vector spaces over for finite dimensional vector spaces over a finite field, and those would correspond to independent sets in unions of classes of graphs that arise from the Grassmann scheme, for example. So there's lots of other variations on this problem you could study in relation to the Lovász number. Might be able to find examples showing large ratio, and also find examples where the Lovász number equals the independence number, and then you can get some sort of determination of what the Shannon capacity of the associated graph would be. Okay, all right. Well, that's what I prepared for today. Thank you for your attention.
Thank you for your talk.